Light exists around us in myriad forms as one of the key elements of our lives and technology. Light plays a critical role in many areas such as information delivery, imaging, communications, healthcare, environmental sensing, energy production, and manufacturing processes. Photonics is instrumental in controlling light effectively. It is a fusion of optical technology and electronic engineering, focusing on using light to create, control, and transmit information. A notable application of photonics is in optical communications. Light can travel faster than electrical signals, making it an ideal medium for high-density data transmission. Data can be transmitted through lasers, optical fibers, and photonic devices, which is the pillar of modern communications technology. Photonics enables faster and more reliable internet connection and telecommunications services.
Light plays a crucial role in our modern technologies and applications. To effectively manage and harness this light, materials called waveguides are essential in the field of photonics. Waveguides are the fundamental platform for moving light reliably. They play a key role in diverse technologies and applications dealing with light-related information. For example, we can guide light rays along specific paths by implementing optical components like optical fibers and laser diode on waveguide. We can also enhance the performance of optical device by integrating optical lens or optical modulators on waveguide to control the amplitude and phase of light. Our team has been conducting research on waveguide based on thin film materials. We are particularly keen on finding out what happens to the optical functionality of a waveguide when thin film materials become increasingly thinner. We demonstrated for the first time in the world that waveguide can transport light in a reliable way, even when their thickness is ultimately as thin as an atomic layer. We have discovered that we can explain this phenomenon intuitively and quantitatively using the wave mechanics analogy between light and electrons.
The waveguides developed by the team are two-dimensional semiconductors called transition metal dichalcogenides that are packaged in a polymer environment. Considering that the two-dimensional materials, the core of the waveguides, are less than 1 nanometer thin, the material's properties are changing in a very small area from the perspective of light with a wavelength of hundreds of nanometers. In quantum mechanics, we use the delta potential to predict how matter waves behave when the potential energy in these extreme areas changes suddenly. Based on the fact that light also shares these wave mechanical principles as an electromagnetic wave, the team was able to interpret light behavior in atomically thin waveguides in terms of delta potentials for photons. Based on this theoretical interpretation, the team has successfully developed high-performance waveguides by precisely establishing the process and experimental conditions necessary for developing very thin waveguides. The two-dimensional semiconductor-based waveguides developed by the team can reliably transmit visible and infrared light within a propagation length of up to centimeters. This breakthrough represents an innovation that surpasses previous studies by several hundred times. Despite numerous global efforts to use atomically thin waveguides as a platform for photonic integrated circuits, the team's achievement is the first in the world to achieve this goal.
The chip-scale propagation lengths of semiconductor devices are necessary to utilize waveguide as a platform for photonic integrated circuits. Our research team was able to accomplish this challenging goal based on a thorough understanding of the guiding mechanism of light. Furthermore, utilizing waveguide as a platform for photonic integrated circuits requires not only long-range propagation lengths, but also diverse underlying technologies to control the property of light within materials. When waveguides become very thin, the controlling principles and techniques that have worked smoothly in existing systems stop working altogether. Our team has suggested new principles to control the trajectory, wavefront, amplitude, and diffraction of light transmitted along atomically thin waveguide. And we are researching the potential of those principles. In particular, we are working toward developing more complicated and advanced optical functionalities by integrating the optical component necessary to control light on waveguide, like we do with Lego. Using this method, we plan to gradually create a step-by-step system for optical integrated circuits based on this atomically thin waveguide.
Studying waveguides at the sub-wavelength scale, much thinner than the wavelength of light, requires the crucial technology of growing atomically thin films uniformly at a wafer scale. As we can grow these thin films stably using the current semiconductor process technology, the research on atomically thin waveguides is expected to see a significant acceleration. Professor Myungjae's team's groundbreaking achievement has been published in the world's most prestigious journal, Science. The team was recognized for being the first to demonstrate large-scale atomically thin waveguides. They suggested that thinner waveguides can overcome the bandwidth limit stemming from structural dispersion, laying the foundation for controlling the information transfer of light through the stacking process of thin film optical elements. This research is expected to be the foundation technology for developing next-generation photonic integrated circuits, which can overcome the physical limitations of existing systems. Hopefully, the Department of Materials, Science and Engineering at Seoul National University will develop outstanding technologies which can drive significant advancements in the photonics industry.